So we looked at current flowing through a conducting wire. That was the first hand rule is when the wire is straight. The second hand rule is when there is loops. And that either or produces a magnetic field around that wire. So that means that a moving charge, because we're either moving electrons or a positively charged particle through this wire, a moving charge can produce its own magnetic field. Okay? And a particle moving through that magnetic field will be deflected based on the charge, based on the magnetic field. So here we come to our third left-hand rule. This one's a doozy. Pay attention. To determine the direction a charged particle will move, we need to use our entire hand now. The thumb is going to point in the direction the particle is moving. Okay? Our fingers are going to be in the direction of the external magnetic field. So into the page, out of the page, however we want to do it. You will become contortionists, moving your hand around. The palm faces in the direction the charged particle is forced to move. It's like doing a palm slap to the forehead. If I hit Avery in the palm with my palm and I'm going this way, Avery's head's going to go backwards. It's a palm plant. Okay? Not that I'd ever hit Avery because she's a kind, gentle soul. Okay? Remember, if it's a conventional current, we're going to use the right hand. See how I still have markings of a positive sign on my hand? And a -1 on this one. If you don't know your lefts and your rights, now's the time. There's a reason why we start this before kindergarten and we teach it to you every year, is for this very moment in time in physics. Okay? All right, has nothing to do to make sure your shoes fit comfortably or anything like that, just so that when you hit physics 30, you will be successful. Okay? All right. So if the blah blah, if the charged particle is moving straight up and the magnetic field is initially pointing towards the east, then I would say that the deflection of the charged particle is going to be towards the smart board. Okay? So 3 pieces of information now. Direction that the charged particle is moving, direction of the external magnetic field, and the direction of the deflection of the charged particle. Which way is it going to move? I know. A charged particle moving perpendicular to a magnetic field can be forced in a circular path. So if I have a magnet like this, which way is my magnetic field going to go? It's going to go from the north to the south. Okay? And here I have a positively charged particle that is moving this way. Okay? What is the direction of the magnetic force? Okay? Or force M. Yeah, so you're going to take your right hand, because this is a positively charged particle, you're going to put your thumb in an upwards position, and if you want, you can hold your paper up like this And so you would see that the direction is going this way. My magnetic field is going this way. This part of my palm here, this is north and this is south. So my magnetic field is going this way, which means then that the charged particle will be deflected out of the page. Okay? So here it's moving this way. This is north, this is south, so it's moving this way for the magnetic field. My palm of my hand is right here pointing out of the page. And so then force magnetic is going to be out of the page. Okay? And we needed to remember to use the right hand because it was a positive particle. Force magnetic, that's what the palm will tell you. Okay, here's another option. Okay, what do we know about this magnetic field? It's going into the page. Okay? As it comes in, so it's going into the page and the electron is moving this way. So initially, the electron is going to come and be deflected this way. Now that it's what? The electron is entering into this field, right? So here it enters into the field and the field is going into the page, right? From the north to the south. So it's going into the page. And so initially the electron is going to be deflected down. As we go through this motion, at every point that it changes, we're going to see this circular path happen. Okay? It'll be down, then it'll be this way, then it'll be this way, then it'll be this way. So here's the down part. When we get here, it'll move this way. Right? Here, let's pause. Okay? So this is the key piece here. When I initially wrote down this black arrow, I was using the wrong hand. I was using my right hand. It's an electron. It has to be the right hand. Left hand. Has to be the left hand. Sorry. Has to be the correct hand. Has to be the left hand. Okay? There's lots of questions. We need to practice. The strength and magnitude of the force acting on the charged particle can actually be calculated when it is perpendicular. If it is parallel, there is no magnetic force happening. When it is perpendicular, so Fm, magnetic force measured in newtons, Q is the charge of the particle, unit is in coulombs, V is the velocity of the charged particle, perpendicular. Highlight those words because you will miss this. To the magnetic field, and B with the perpendicular sign because it's got to be perpendicular is the magnetic field strength, and it is measured in Teslas. Mm-hmm. Okay? Tesla was along long before Elon Musk. Okay, an alpha particle. We know what an alpha particle is. It is positively charged. It's shot between two parallel plates. Oh, we've seen this before. That have an electric field strength of 9.77 times 10 to the negative 4 newtons per coulomb. A magnetic field is applied to the parallel plate so that a magnetic field is perpendicular to the particle's motion. If the magnetic field strength is 4.9 times 10 to the negative 7 Teslas, feel like we could make a TikTok dance out of the left-hand rules. What is the speed at which the alpha particle must be traveling so it passes through undeflected? Oh, man. Speed being magnitude only. We don't need a direction. So there's several key pieces in here. Alpha particle, we know that it's positive. We know its mass, 6.65 times 10 to the negative 27, I believe. Q is 3.2 times 10 to the negative 19 for an alpha particle. We know those pieces of information. They're on our data sheet. Two parallel plates. So two parallel plates, positive, positive, negative, negative. Here comes my alpha particle. It's going to go that way, right? That's the symbol for alpha. It's the fish. Okay? And it has to be, the magnetic field has to be perpendicular to the parallel plates so that the magnetic field is perpendicular to the particle's motion. It needs to go through undeflected. Another piece of information given to us. If it is undeflected, is there a magnetic force? No. If it is undeflected, force net is equal to 0. No, sorry, force net. Okay? Now, information given to us. Electric field strength. The Teslas, the magnetic field strength is 4.90 times 10 to the negative 7. It's asking us to find velocity. Okay, we also happen to know Q. And mass. Can somebody confirm the mass for me? I don't have a data sheet. Okay. For serious? Okay. All right. It's asking us to find the speed. So in order for us to calculate speed, we know that we see that here. This is how we calculate speed when we're dealing with magnetism. Okay? We have this. We have the charge. V is what we're looking for. Do we have magnetic force? No, but we can find it. Force net would be equal to force magnetic plus negative force electric. And they're got to be in opposite directions. If they're in the same, it's not going to work. Okay, this here, the force electric is moving down. Okay, force net is 0, which means that force magnetic would be equal to force electric. Or force magnetic is equal to if you write it in the opposite, so that you get positives and positives. Okay, so how do I solve force electric? EQ is equal to FE. Are we have that information? Yes, we do. So it's just a matter of plugging in information. Force electric is equal to what? No, but the actual value. Now that I have force electric, I know that my force electric is equal to my Fm. So I'm going to have 3.1264 times 10 to the negative 22 newtons is equal to 3.2 times 10 to the negative 19 multiplied by my velocity multiplied by 4.90 times 10 to the negative 7. So my velocity then would be equal to 1993.8776 meters per second. When I go back to the question, I get 3 sig digs at the most, 1.99 times 10 to the power of 3 meters per second. An electron at rest, some keywords there. An electron at rest is accelerated to the east by a potential difference of 1.7 times 10 to the 3 volts. The electron then enters into a 0.250 Tesla magnetic field directed south. What is the magnetic force acting on the electron? Okay, we have a couple things happening there. If we have potential difference, it means we have parallel plates. And the reason I'm setting it up this way is because we have an electron that is going to be directed towards a magnetic field that is directed south, which means it's got to go this way. Okay, so this is our magnetic field here. Our electric field strength is going this way. Our force electric is going which way? Which way is our electron going to move? Okay, our force electric is going to the right. And it's accelerated, or it's at rest. So our VI is 0. It's an electron. Code word for we know the Q. We know the mass. Yeah, negative 19, yeah. It tells us the potential difference. And it tells us the magnetic field strength. Okay? What is the magnetic force? So, how do we solve for magnetic force? No. QVB. That's how we find force electric. Okay? Now, we need to be able to figure out V. We have Q, we have B. V, speed, because it's accelerated. Here it's 0, but by the time it hits here, it's in motion. So we need this. What would we call this? If this was VI, this would be VF. Where do we get VF from?
Delta E.
Delta E. EKF minus EKI. Where are we going to get delta E from?
E equals delta E over Q.
Okay. This piece here, we know that the initial velocity is 0, so we're not going to have EKI. So delta E is going to be equal to 1/2 mvf squared. And this piece here is what we're looking for, that VF. That's what we want out of these couple of equations. So delta E is going to be equal to delta VQ
J.
Okay, now I can figure out EKF. Force magnetic. Okay, 9.77 times 10 to the negative 13 newtons. Now we got to figure out what is the direction. So when I look at it here at this particular point, my magnetic field is going north to south and my electron is moving left to right. So my direction that it's being deflected is
Out of the page.
out of the page.